There we go. Pretty sure it says recording in progress or something like that. All right, okay. You cannot minimize when you're recording this meeting. Awesome. Okay. So yeah, so we have this problem 2 of the practice questions, module 9. And we have what it seems simple but very complicated thing that we do all day, which is breathing. In this case, 20 degrees Celsius air, which is dry, which now happens here in Florida. It should be something else like Arizona or something like that. But well, let's keep on doing that. We are getting air in. I'm just looking at the map right now. I'm not reading the problem yet. We have dry air that we're breathing in. And then in our lungs, we have water. That water then becomes what we call saturated air. So we have water vapor. That's what it means. Okay. So essentially what we have here is breathing dry air, spitting the same air because plus some water. So let's see now what the problem statement says. Let's estimate the rate of heat loss during breathing. Okay. Good. An average person inhales about 6 liters per minute of bone dry air. So no water, 20 degrees Celsius, and exhales air saturated with water vapor at 37 degrees Celsius. So whatever our normal temperature is. For this exercise, let's assume steady state, non-known flow work, potential and kinetic energy changes are negligible, no reactions, air is an ideal gas, and the mass of the air is changed. So we have some information. We have the molecular weight of the air, which is 28.84. We have the density of air. We have also the rate, well, not the rate, but the proportion of water with respect to air that we're going to have when we exhale. So let's start working on the problem. So I was saying earlier, we learned this far, we can model this with a box. We are a box, or we are going to become a box once the end of our life is coming. Well, anyways, I meant to say a coffin, but it got really dark. So anyway, so here we have dry air. Let's focus. Dry air coming in, saturated air coming out. Awesome. So we know that, very interesting from the problem statement, that it's steady state. So we know that whatever air they're telling us, which is 6 liters per minute, it's going out. So something that we can do really easily, well, before doing that, is to highlight the information we have. I always forget that. I get very excited with this problem. So as I was saying before, we have some air coming in at a temperature. We have some saturated air coming out at another temperature. Let's see what else I was talking about. We have a bunch of data over here. I'm going to highlight. It wouldn't be wise to not do that. And we have a couple of questions. The first one being, by the simplified energy accounting equation, then calculate the change in specific enthalpy. There's those warming dry air from 20C to 37C. So in this case, at least for question B, what we're just looking at is at this portion, which is just warming the air, not necessarily putting water in it. Specifically, if I want to be very precise, just this portion. Over here, not really including water, all right? And then we have to calculate the rate of heat loss. So let's start working on that. We already highlighted, and the first thing that I want to do is rewrite some information. So what we're getting here at the beginning is volumetric flow rate. We know how much air is coming in. So we know that is that volumetric flow rate of air coming in, it's equal to 6 liters over minute. From our first test, we know that from here we can calculate mass, because mass flow rate, forgot the little hat. Mass flow rate is not only that the volumetric flow rate times density. So I'm gonna write that really quick over here. Air coming in, it's equal to the density of air times volumetric flow rate. And very handy dandy, we have the density over here. So we can now know what the mass in air is. Also, the reason I'm doing this is because in the problem and the questions, we have a specific enthalpy. And then specific enthalpy is the enthalpy or the enthalpy change divided by the mass. But then they're talking about the rate heat loss. So you gotta start digging in the future that we're gonna basically use mass to transition from the enthalpy that is specific to the mass to actual just a total energy that we're losing by breathing, okay? So that's the reason I'm calculating the mass right here. So if we do this, we're gonna get, I think the 0.0, okay. So 0.002 grams per centimeters cubed, and centimeters cubed is the same as a milliliter. So we can just say milliliter. And we know that 1,000 milliliters is a liter, so we can write the 6 liters over minute as 6,000 milliliters. Usually I like to use the same unit. Sometimes some people don't and they get confused, but I like to do that. I recommend you do the same so you don't get confused. So if you calculate that, the answer to that should be, I didn't write it here. Awesome. See if I can. No, I do have it. The answer to this is 7.2 grams over minute. Awesome. So we have the mass flow rate of air coming in. Why is that useful? Because we also know the mass flow rate coming out since it's a steady state system. So this is the same as the mass flow rate of air coming out. And funny enough, from this, we could also calculate the mass of water coming out, since we know that we have this over here. So we know that for every gram of dry air, we have 0.041 grams of water. So we know that water coming in is 0, given our the sign over here. We don't have any water because it's dry bone air, but we definitely have water coming out. So the mass of water out is going to be equals to the mass of air, grams of a minute of air. And we know that 1 gram of air, for every gram of air, we have 0.041 grams of water. And this should be equals to 0.295 grams per minute. Awesome. It's going to be very important information that we're going to use later on in our endeavors. Okay. So first question, let's go back. Write simplified energy accounting equation. So we know that for the accounting equation, we have heat, we have enthalpy change, and we also have work, non-flow work. In this case, based on the problem statement, we don't have non-flow work. So we can start writing the energy accounting equation as the following way. So energy accounting equation, it's going to be equals to negative enthalpy change, or the rate of enthalpy change, plus the sum of the rate of heat transfer, plus all the work, the non-flow work, which this stuff like you can think of a shaft or something being applied to the system, or the system applying energy to something else. And as I was saying before, this guy over here is equal to 0. So we ended up with this equation that the heat transfer or the heat loss is plus the rate of enthalpy change is going to be equal to 0. So we can start foreseeing that what we're looking at, or what we're trying to get to, which is our final question, calculate the rate of heat loss, is going to be equal to the rate of enthalpy. So we need that to end our problem, okay? Let's circle this question. And that should be the answer for A. Okay. Okay. Gonna just pause for a little second because I see some people are writing down, and we're gonna continue. All right. So yes, I put negative. Oh, I didn't do that on purpose. That's not correct. Thank you. Yeah, I'm a human. Thank you so much. Yeah, I usually commit a lot of mistakes when I'm teaching something, so please go ahead and correct me. I will get happy because I don't want you to misunderstand this and then fail the class and be super, like, get out of college or stuff like that. We don't want that. Yeah. Yes. I the mass fluid. Why would you do that?
Because that is the enthalpy, and then when you do mass flow rate times something is the specific enthalpy. So that is the sum of enthalpy in all the steps.
You mean like this, right? When you have the hat
The hat.
and you are multiplying by the mass. So this guy, it's equals to the enthalpy. Oh, this is obviously changed because we cannot calculate the specific, like 1 point of enthalpy divided by the mass. So when we have a specific enthalpy, we multiply by the mass to get this guy. I don't know if that was confusing or not.
Right,
but-
the rate of change in enthalpy. So the one with the dot is the rate of change in the enthalpy. And then the one with the hat is the specific enthalpy. So those two are different. Ultimately, so mistakes. So make sure you, like, whenever you make your equations, you have them like different things.
Yeah. Essentially, hat means divided by mass. That's about it. All right. Is that cool? Thank you. All right, let's go for B. We're killing it. Okay, so B, what it says is calculate the change in specific enthalpy that results from warming dry air from 20C to 37C. So in this case, this path over here, right? And this is something that you have to keep in mind. We're talking about air, and air is a gas. Therefore, since we're talking about gas, we have to do the polynomial that we were chatting about in class. So that's going to look like this. So if we name this path over here, I prefer numbers than words. So let's do change here. So it should be the enthalpy, specific enthalpy path 1. We can call it like that because we're cool. And just that's going to be equals to the integral of T0 to Tf. And we know that T0 in this case is going to be 20 degrees Celsius and Tf is going to be 37 of, I forgot exactly what Cp meant. My apologies for that. Thing is the specific heat capacity. Thank you so much. Like inorganic chemistry, but I forgot names. Thank you. Well, yeah. So this is going to be equal to our initial temperature, which is 20, final temperature was 37, and our polynomial, which we know that is A plus B temperature plus C temperature square plus D temperature to a third differential temperature. Okay. And this coefficients A, B, C, and D are coefficients that you're going to be given in the exam. And if you need that for homework, you have to go to the book and go to the appendix, and you're going to be able to find them. For this example, I'm going to give them to you because I try to be a good LA and not make you suffer with that paper thing that we don't like, which are books. Okay. So let's go for it. So the first one is 28.94. If we take the integral of A, it's going to be T with respect to T. Then for B, it's going to be 0.4147 times 10 to a negative 2 T squared over 2, because we're integrating T. Third, it's going to be C. C, it's equal to 0.3191 times 10 to the negative 5 t to the third divided by 3, because we're integrating t squared. Finally, d, it's going to be 1.016 times 10 to the negative 9 t to the 4 divided by 4. And the limits of this integration is 1 to 37. Something to keep in mind is that you can see here, as we go this way in the coefficients, we know that they affect less, and oh, this is positive, my bad. They affect less, and for the enthalpy. So yeah, there's something interesting that happens there. And the units for this are joules over mole and degrees Celsius. So we are going to end up just with joules over mole. So by solving this, we're going to get that the specific enthalpy of that first path of just the dry air heating up from 20 to 37, it's going to be equal to 494 joules over mole. Okay. With that, it's good, but remembering that we were like foreshadowing this type of math in the future, we have to transition from moles to grams. So let's see what we can do for that. With that, we have the molecular weight of air. So we can use that to transition effectively from moles to grams. So let's do that. So here we're going to multiply by 28, I think, 2884. Yeah, 2884. So it's going to, oh, no, sorry, divide. Yeah, because it's 2884. So grams for each mole. So we can cancel that out, and we're gonna get 17.39 joules per gram. That's gonna be our specific enthalpy. So this is the answer for question B in this case that I call B. Okay? Yes. Yeah, no, I'm not saying that it has to be. I'm just saying that given the questions that are proceeding from this question, it's useful to have it in grams. Okay. But eventually you have to transition. Okay. So yeah, whatever works best for you. Yeah, it's the same.
Yeah, but usually it's answered in grams. Okay. So you would have to convert it. But let's say on the exam and things like that,
it would stay.
They will tell you.
Yeah,
what units they want to see it on.
Great question.
Yeah, if it doesn't say though, I guess it would be appropriate to ask.
Yeah. Good question. And don't forget to box your answers so we know that you meant to stop there. All right? Okay. Moving on. So we have to go for C now. C talks about the total change in enthalpy. Okay? So we already have, as I was saying earlier, when it said saturated air, that's just some mixtures of air, like dry air plus water. But water in the form of vapor. So technically the air part, it's already done. We already did the heating process of that. What we were missing in our adventure here is getting water from being a liquid here to being a gas over here. So we have to do a change in phase. I mean, a change in state. Okay, I almost did it incorrectly. Okay, so we have to do that. I would like to change this to this. So the specific enthalpy too. So let's see. So I was saying earlier, or we were discussing earlier, that a specific enthalpy is just the enthalpy rate divided by the mass. So to calculate the total, we only would need the sum of the change of enthalpy. Oh, we can do it this way. Let's make it this way. So for a specific enthalpy, the total specific enthalpy is going to be equal to the change in specific enthalpy in the first path plus the change of specific enthalpy in the second path. If we multiply this, like each of those by its specific mass, we can get the total enthalpy, which is what we're trying to calculate. So multiply this by total mass. In this case, we're multiplying this by the mass flow rate of air, which we only talk about here. And this one, the second path, we're going to multiply it by the mass flow rate of water out. So as you can see, we already have this value. We already have this value, and we just calculated this value. So we're just missing this guy to get the total. So that's the reason I have this table over here. So if you go to this table, we have, towards this side, we have the enthalpy in kilojoules over kilograms, which is the same as joules over grams, because it's just multiply and divided by 1,000. So if we go here and we look at this column over here, which is the temperature, we see that we have the temperature of 38 and 36. If we do this, what I ended up here are temperature or specific enthalpy for the water vapor at 36 and 37. So if we do a simple average of these two, we will get that the specific enthalpy for water vapor, it's going to be 2,416, 14.05 joules over gram. So we can use that new information and finish this equation over here. It's going to be equal to the first one that we calculated as 1739 joules over grams times the mass of air, which was 7.2, I believe, grams over minute. Just gonna check really quick. Yeah, 7.2. Okay. Plus the specific enthalpy of water, which we just calculated up here to be 24.
That makes sense. Do you guys get where he got that?
Oh, yeah.
2,414?
Yeah, please stop me if you know if I'm going too
That makes
fast.
sense. Okay, you're just taking an average because you don't have the exact value for 37 degrees.
Yeah, we're trying to
So your
calculate
average is 36 and 38.
that value. Good. So 2414. So we get here 2414.05 joules over grams times whatever it was for water, which I think is 0.295. 5 grams. Okay, so the enthalpy change total is going to be equal to 837.35 joules per minute. Okay, and now if we go again to the energy accounting equation, like this part over here, we see that the heat transfer, the heat loss is going to be equal to the change, the enthalpy, the rate of enthalpy change. So we can just write that again. So D from energy counting equation, we know that the rate of heat transfer, the loss, is going to be equal to the enthalpy rate of change, which we just calculated to be 837.35 joules over minute. And that will be our final answer. any questions? Okay, we have your quizzes over here. And I need to find a way of making this recording get to you. It gets hard for me because I'm not like a faculty, so I need to like download it, send it over to Dr. Pora. So I'm gonna stay here for a while in case you have any questions. But yeah, you can enjoy your Thursday if you decide to do so. Thank you for coming.
This module has more problems that Dr. Porras will upload, so